Good to go. How's everybody? So by the donuts, we once again have like paper and pen if people want that. If you guys can recall back to last time. Which ones do I turn? Okay, there we go. If you guys can recall back to last time.
Right?
Too delicious. You're going to recall back to last time. We were trying to like map out on paper an algorithm before we try to put this into Python to see kind of if we can do that. And our ultimate goal was to come up with a plan, a procedure, an algorithm, if you will, to find all the numbers, all the prime numbers 2 through 20. So I believe where we were when we left off was we had said, all right, we need some kind of loop that goes from 2 up to 20. We're skipping 1 because we know that that can't be prime or non-prime. It's just a weird thing. And then we had decided, all right, so then what we need to do is say we're like testing the number of 14 or something like that. We need to go from 2 up to 13 and basically do something, right? So that's where we are right now. So, all right, we said we're going to loop from 2 up through 20, and then whatever number we're currently on, say it's like 14 or something, we're going to go 2 through 1 less than that and do what?
Divide it.
What's that?
Divide it.
Divide what by what?
Yeah.
Okay, yeah, so we really want to see if the candidate, prime number is divisible by the candidate, it's divisor, right? Divisor. If it divides evenly, right? Which would mean, I think Katie, you said it, like use the modulo. So we're going to test if that is 0, right? Basically, if there's no remainder. So we'd say something like, so let's go in a level here. So test if candidate prime is evenly divisible by candidate divisor. So that's one thing we're going to do.
I have a question.
Yep.
Is the equals sensitive, or is the modulo sensitive to decimals? So what if you have something? Oh, actually, that's modulo. I'm confusing.
That's all right. I mean, I think we did a little bit of this before, but we can revisit. So if you had something like, so what do you want it? So if you want to do something like, are you saying like 2.0 modulo 0.4, something like that?
Yeah.
Well, so there you're going to have some kind of weird rounding error because of like the imprecision of floating point numbers. But in theory, yes. So if you did something like 2.1 modulo 0.4,
Right.
like you can do that. It's going to have some rounding errors, which is unfortunate, right? Because like, when you try to do 2.0 modulo 0.4, really that should be 0, but it's actually, because of the imprecise way it represents decimal numbers, it's actually going to give you 0.3999999, which is like kind of the worst result, right? Like it's the farthest off you can be. But that's life. That's why you don't use floating point unless you have to. But yeah, it can do that kind of thing. Usually, like more often than not, we use it for integers, but you can definitely do it for decimals. And it doesn't really matter here, right? Because here we're only worried about integer math. Okay, so now let's think a little bit more. So when we say test, this is where we have to start thinking a little bit more like the computer and less like the human. So what are we going to do if the prime, or if the divisor does or does not evenly divide into the candidate prime number?
Check the next number.
Well, in each of these cases, what do we do? So what do we...
We print prime if it's prime.
Well, when do we know it's prime?
If the modulus is 0.
So if I'm testing, let's say I'm testing to see if 14 is prime, and I first start with 2 as a candidate divisor, it evenly divides. Well, let's do it this way. I'm testing to see if 13 is prime, and I test to see if 2 divides into that, right? Because that's the first one in that inner loop, that second loop. So if 2 does not divide evenly into 13, what do I do? All right, then we go on to 3. If 3 doesn't work, we do what? Go on to 4 or 5. So we keep going up the loop if it doesn't divide. And what if it does divide? So if we're testing 14 and 2 divides evenly into it, what do we do in that case? We what? Okay, so we know that that's not prime at that point, right? So depending on how we want to represent this, let's say we just want to print out whether it's prime or not prime, right? So we could say something like, if it is divisible, we could say something like print not prime, right? Because as soon as we find one divisor, we know it's not prime, right?
How do we logically stop the loop then if it's not a prime number? So if we're checking the statement and it's always false, then how do we tell that once you hit this point in the loop, just stop and then print not prime?
Very good question. Sorry, mouthful donut.
Can we do an else statement or something?
So this is where I think the paper kind of starts skimming. So if you were doing this on paper, how would you kind of represent that you were doing this? You don't have to actually do this with variables and stuff, but if you were doing this on paper, how would you maybe keep track of what you're doing here?
If the number is greater, if the divisor is greater than or equal to 1, then you stop it. So once you hit that actual number you're at, so if say we're checking 13, once we hit 13, we know to stop. So if it's equal to or greater than 1, then we stop the loop. Or is that not efficient?
Well, we can, okay, yes, so we can stop the loop. That's one way to do it.
But we are saying the numbers 2 through product value minus 1. So wouldn't it already stop?
Oh yeah, so the loop, but yeah, so by the definition, the loop will go through all the numbers.
Yeah.
Now we could terminate the loop, although there are also ways to do this without force stopping either of the loops. Well, so I will. Well, so what would we? So let's do it. Let's think of it this way. Let's say I have. Let's say I have a list of the numbers I'm going to check. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Right? This works better on paper, obviously, but let's put it on the screen. All right, so let's assume we've already checked a bunch of these others. Let's say we're already up to 12 in the loop. Okay? So then we say, all right, we're going to eventually loop through what? We're going to loop through 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? Actually, you know what? Let's make this slightly more interesting. Let's say that we're checking 15 right now. Okay. So we're going to start looping through these numbers. We're going to say, all right, is 15 divisible by 2? No, right? So the loop could go on to 3. When it's divisible by, I'm trying to figure out a good way to say this without leading too much. So when we find that it is divisible by 3, we know that 15 is not prime, right? So if I were doing this on paper, I guess what I would do is I would somehow cross 15 off my list of possible primes, right? As soon as you find a factor, it's eliminated, right? So, all right. Well, this may be a little tricky to figure out in Python if you haven't done a whole bunch of this stuff yet. But maybe let's start doing some Python here and see if we can figure it out. So let's actually start up PyCharm. I think we can do this with what we've got so far. Take a second to load up because PyCharm is slow. It is February 29th, so I thought we could, if we had time, we could also do some fun stuff with leap year madness based on some of that date stuff we did before, but I guess we'll see if we have time. All right, so let's try, let's do a new file. Let's call this prime finder or something like that, .py. Okay, so let's do this. Let's move this guy over like this. And let's put this over here. Okay, let's put this on this side, the other thing on the other side. All right, that lets us see our notes. Okay. So what would we do? All right, so if we're doing this in real Python, we could do something like this, right? So we could do something like for candidate prime in, so if we want to go 2 through 20, how would I express that? Do you guys remember? Well, let's see.
Did you have to create a list?
Range. Is that going to give it to us? 221, right? Because it starts at the first number you specify and ends at the number you specify second minus 1, right? So range 221. Does that look familiar to everybody? Remember your colon. And then we had what? We said for the numbers 2 through current value to check. So we could say like for candidate factor in, so what would we, how would we express what our candidate factors are going to look through?
In range, parentheses, candidate prime minus 1.
Close.
Plus 1?
2.
So we want to start with 2, right? Because we don't want to test 1 because everything's divisible by 1. And what's the end of that range going to be?
Candidate prime.
Yeah, it's going to be candidate prime, right? Because that's actually going to go through candidate prime minus 1 because of the dumb way that range works in Python, right? So actually, that's not going to end on candidate prime. It's going to end on candidate prime minus 1. All right, so let's just do this like a way that's actually not going to work exactly, or not going to work exactly like we think. But let's just do it this way, and then to see how we can fix things. So we said like, oh, I can look at that screen. That's much easier. So if candidate prime modulo, did you get it working already? Are you already ahead of us?
Show off.
Candidate factor equals 0. I put those. Can't remember if we've done parentheses yet, right? But parentheses work just like they do in math, like PEMDAS. You technically don't need them here, but I find that easier. So if we do the remainder of candidate prime divided by candidate factor, and if that is, remember, double equals, right? We're testing equality. If that is equal to 0, we've done ifs in here, right? I'm not like hallucinating. Okay, cool. Let's just do this. So let's say print not prime. This is not going to work exactly the way it's supposed to. Have we done else? We haven't done else's though officially in here, right? I don't think we have. So if it can be one thing or the other, we can do this thing where we don't have to test explicitly to see if candidate prime modulo candidate factor is not 0. We can just say else, right? Which is the way that we say like, if it's this thing, do this. Otherwise, right? So else just lets us do the something if the thing that's in the if is not true, then we do the thing under the else. Okay? Print prime. Okay? So again, this is not going to do what we think we want to do. Let's see what it does in fact do if we run this. And then maybe we can figure out ways to improve it. So let's run prime finder. Oh, you know what we should probably do? What we should probably do is say print candidate candidate prime, candidate prime, so we know which ones we're on. And print candidate factor, candidate factor. Okay? Is everybody kind of on the same page so far? So let's try running this guy. I think that's this here. Let's just do this. Okay, so this is what we've got so far, which is not going to be true, but let's see what it's going to do. Let's just go to, let's see. So candidate prime, let's go to like when we're testing 16. So what it's doing right now is saying that candidate factor 2, not prime. Candidate factor 3, prime. So it thinks it's doing it this way, it thinks it's prime every time it doesn't divide, and thinks it's not prime every time it does divide, right? Which is not exactly what we want to do, right? We probably just want to print like once whether it's prime or not prime, not like whether it divides each time. So can we think of some way to do that without changing the structure of this too much?
You can do the while statement. So instead of if, you can say while this is true. And then once it is, wait, let me think about it. So once it is true, you can stop the loop.
So that's one way we can do this. So while what is true, would we keep looping?
Well, it's not.
Right, while, so basically we only need to do this while we have not confirmed that it's non-prime, right? So we only need to keep checking as long as we've confirmed that it's not prime. Let's table that for a second because that's going to require us changing that second for loop to a while loop. We can actually do this, it's just not going to be super efficient without changing that while loop to anything else. Can you think of another way to do it? We'll have to like take out these prints and such. So how can we keep track? So one thing we could do, right, is just like keep track as to whether we had found any evidence that it was not prime and just print out that result at the end, right? So how could we do that?
Depends how you want it delivered. Like if you want everything at the end, you can just store it somewhere.
Ah, store it somewhere. That's what I was looking for.
Ah.
All right, so let's say we create another variable to indicate whether this current thing is prime or not. So how would we do that? So we said like basically we want to
Maybe have the list then? Go list.
well, we could do this with lists, but we don't need a list. We technically, except for the range statement, we haven't technically talked about lists exactly, although you kind of can see them and work with range. We actually just need like one single variable each time we run through this loop to do this. So, so prime is kind of like guilt in court, right? That you're prime until proven otherwise, right? You're like innocent of primeness until you're proven guilty of having a factor. So we could do something like this, right? So we could say, let's say something like is prime equals, let's see, in Python, true is capitalized, right? So we could say something like this. So we could assume when we start off that the value is prime. And then what do we do here under this if statement?
Else.
Well, we actually won't need an else in this particular circumstance. And actually, an else would probably screw us up if we're doing what I'm planning on doing. So now what we're going to do is start off with each candidate prime, assuming that it is prime. So assuming that like the value that tells us if it is prime or not is true. But then we're going to check all these factors, and if we find one that divides evenly, what do we decide?
Changes from false.
All right, so if we did that,
But I guess with this, like we won't know, we just know the number of prime numbers. We won't know like the actual value. This is just like a counter variable, like.
well, so right now, yeah, we haven't done anything. We were just tracking whether or not it is prime. So then what could we do to actually print out when stuff is prime. So we want to somewhere like print out when is prime ends up being true. We want to print out something that says it's prime, right? Where could we do that?
Right there.
Okay. So,
If candidate,
and this is where we have to be careful. So when do we want to finally assess that is prime? Like don't worry about like it's sort of where it goes in the text, but like just intellectually, like conceptually, like when do you want to assess the final value of that is prime variable?
when it's reached the end of the range of possible values that need to be checked.
Okay, yeah, so when we've checked all of the candidate factors, right, it has had every opportunity to be proven not prime. So we would do it like after this whole inner for loop wraps up, right? So the tricky thing, right, is that in Python, like all of our indications of where we are in the program are done with indenting. So if we want to do that, we want to make sure that we indent it so like it runs through everything that's indented relative to this for loop, right, before it goes on somewhere else. So we want to do this down here, right? So we want to say like if is prime, print prime. And here is where we can put an else, right? So
You're missing the false, right? I mean,
well, we could do it. I was thinking of doing it here, but we could do it.
Well, how does it know which one to print if you don't, if the if statement is a
Yeah.
contingent on like
Yeah, yeah, no, true.
Well, okay, so this is. Oh, I see what you're saying. You want me to say if is prime is true? Sorry, that was me skipping ahead a step. So let's try this. All right, so if I do that, I think we might have briefly gone through this, but I don't expect anyone to remember. So if you have a value that can be either true or false, and you test to see if it is true or false, so like what I just did there is I created a value called is prime and set it equal to true, right? Then I tested to see if that is equal to true, and the answer is true. Then I tested to see if it's equal to false, and the answer was false.
How is that possible?
it's not equal.
Well, is true equal to true? Yes or no?
Yeah.
Is true equal to false?
No.
Is false equal to false?
Yes.
Okay. So if you have something, So-
Tricked me.
no, I mean what you said is all right.
Okay.
So if I did this now, now I'm going to confuse myself. All right. So when your variable is true and you test to see if it's equal to true, the answer comes out true, right? Like true is equal to true. True is not equal to false, so the output is false. Now, if your variable is the value false, is that equal to true? No, false, right? And if your value is false, is that equal to false? Yes, that's true, right? So when you test for equality of a yes-no variable or a true-false variable against the values true or false, what does the output come out to be? So if you test to see if something is true equal to true? True. Is false equal to true? False. So why was I in here not bothering to have a test of equality? Does that make sense?
no.
All right. Sorry. Let's try. All right. So let's try this.
I guess I don't know. I'm not understanding. Like I'm thinking like if it's like if true, how true and false are 0 and 1. So,
Yeah. So don't overthink this too much. I think so. Let's make a shorter variable just called truth, right? So let's say truth starts out as let's say it starts out as true, right? And we say if truth equals true, print true. And we can even, oops, sorry. Else print false. So what's that going to print?
It's gonna print true,
Okay.
right?
Right. So it's going to print true, right? Because truth, the variable called truth is true, right? Now, let's say, well, if truth were false, what would it have printed? If I said truth equals false and then ran that like if else statement again, what would that print? Okay, it should print, yeah, so I can do this again. Let's see. Print true, else, print false. All right, so that prints false, right? Now, prepare to have your minds blown. If truth, print true, else, print false. All right, now why did that print false there when I just said if truth, print true, else, print false?
Does it know like you're trying that the outcome that the variable truth is true false? So like some default in there is like if it's true, print that. If it's not true, then print this.
Well, I mean, I think you're right, but I think we're still overthinking it. Like this variable called truth, like what's the value that's in this variable that I named truth?
It's either true or false.
Right, which is the same as the output. So let's think of it this way. Let's say truth equals, in honor of 1984. Oh, this is an interesting one. Let's do it this way. 2, 2. All right, what is that going to give me?
It'd be false.
Right, because 2 plus 2 is 4. We do that parentheses first. Does 4 equal 5? No, it does not. That's false. So the value of the variable truth will be false, right? So the output of that double equals comparison is a true or false value, right? Do we agree? Yeah.
But then I also assign strings and integers to it, and it also treats it as true.
Okay, shh. That's true, but that's a second stage. But all right, so the only point I'm trying to get through here is what's going on here. What if I say if truth? What does it like? Truth is a name that refers to something. Truth refers to what?
False.
Right. It refers to the fact that something is false. Right. So you don't need a so what happens when you have a condition like 2 plus 2 equals 5 is that returns an output of true or false, right? So in other words, you could also just say something like if true, print is true. And that would happen, right? Because what the if is doing is just looking at the thing right after it to see if it equates to true or false, right? So if I say like do something, if some condition is true, like, you know what I mean? This is so hard to say without like overusing the words.
The double equals is always just checking if something's true or false. That's the only result of it.
Right.
And so like in that statement, 2 plus 2 is 4, it's not equal to 5, it'll be false. No matter whether it's a variable or straight up just you say false, either way the answer is going to be false.
Right. So true and false are just values, right? They're truth values. But they're values just like numbers, right? They're either true or they're false. And so what you do after the if, like if the thing that follows the word if is a value that is true, then you do the thing, right? And true is true. A variable that holds the value true is true. A statement that is true, right? Does that kind of is that making sense to people? So all that is to say is that for any value, if I test to see if that is equal to true, it's just the same as the value itself, right? Or for any expression, right? So in other words, if I say, okay, so let's say this, like, is the sky blue, true or false?
True.
Okay, if the sky is blue, then, do something, right? So if I tell you, if the sky is blue, breathe oxygen or something like that. And then I tell you, if the statement the sky is blue is true, breathe oxygen. That's going to be exactly like logically equivalent to that, right? In other words, if I say if something is true, that's the same as just saying like if and then that condition. Does that kind of make sense to people? So anyway, all of that is to say that saying something like if is prime, when is prime is a value that can be true or false, is the same as saying if is prime is true. Does that kind of make sense? Or is that still
Yeah.
confusing to people?
I mean, just for like my own redundancy, can you put if the prime equals, if its prime equals true, print?
Oh yeah. I mean, so we could have this. This is not wrong. It's just,
Redundant.
it is just redundant with saying if is prime. And it can be useful to actually do this sometimes, especially like I named this variable in such a way that like it's readable, you know what I mean? Like if is prime sounds like, yeah, if it is prime, you know, like when it's true that will read like English kind of. But we can say that too if that makes people feel better. All right, so does this make people feel better to write it this way?
Yeah.
All right, so let's, with no further ado, let's run this and see what happens. Did this work is the question. 2, 3, 4, 5. Are these all right answers?
What number? 17.
Oh, I was just looking at all of them, right? Because this is, so you might notice I surreptitiously commented out the thing where it prints out all the candidate factors. So it's just going to print out the output of each.
Sorry, what's the range? I can't quite read it.
2 to 20.
Prime number. 20 or 21?
Well,
Like those numbers.
Yes.
what's in the range statement is 2 comma 21, but it will go from 2 up to 20. So it went up from 2 up to 20. Did it give us the right answers for all of 2 through 20?
It said 2 is prime.
Is 2 prime? Yes. 2 is a weird prime, right? But because like all the other primes are odd. But the only thing, you know, was it you I was talking to about this the other day? Like how like we think it's weird that 2 is prime, but like there's nothing special about even and odd numbers, right? It's just that like 2 is the lowest of all the prime numbers because it's the lowest integer that's not 1. And so, you know what I mean? There's nothing special about even and odd as opposed to like numbers divisible by 3 or not divisible by 3, except that they alternate every other number, unlike, you know, things that are divisible by 3 only exist every 3 numbers and so on, right? But yes, 2 is prime. We just like often don't think of it as prime. So is that, so we have something that works, right? Is it clear to people why it works? So
Nightmare.
what's that?
Looks like a nightmare.
If this looks like a nightmare, oh.
I mean, it like this can't be the most efficient way of doing it.
Well, so it's not, certainly. It's not horrible. Now, is everyone clear on why? Let's try this and see. You know, we could have had an else up here and said, right, you might be tempted to do this. Like this is a very common thing for a starting programmer to do, right? Because let's say you're checking factors and you say like, if you find a divisor, then it's not prime, otherwise it is prime. But if we do that, actually this may still work, but it doesn't work. No, it doesn't. So if you had that else statement in there, it thinks everything is prime, which is not right.
Why
Obviously.
does it? Makes no sense.
Why does it now think everything is prime?
Yes.
All right. You seem angry.
I am angry.
All right, so this
Looks
is
like-
where,
Like when you first do is prime is true, then like you're turning some of them.
Because you're not terminating the loop, so then,
aha,
like if you did 20, you would still check to 19, and
Right.
then you change it to true because of that else statement.
right. And it turns out that no number is divisible by the number right under it, right? Except for, or no integer is divisible by the integer right under it, except for 2, and 1 is a special case anyway, so we don't check it, right? So there, let's do this debug thing and now see if we can figure out why it's doing what it's doing, if that didn't make sense to you, right? So let's,
Well, like what I was saying, I mean, the way I see it is like, so they all, every number when you come to it, it starts out true, and some of them are made false, but then it, like, I mean, one by one going through the sequence, but then if it's not false, if you automatically turn it back to true, then like, none of them are gonna be false anymore.
right.
Could you simply fix this by using a while statement instead of if statement? So while this is true, keep going through the loop, and then once it's not true, stop the loop.
Yeah, so I think we could rewrite this with a while statement. That's probably a thing that we would like to do. Before we do that, let's just quickly kind of, is this making sense to you or is this so confusing?
No, it makes sense.
Mostly makes sense?
I know we haven't discussed this yet, but if you just use a break in the else, that work as
Yes, I mean, yeah,
well?
so
Would that be the
So
equivalent?
there are ways to break out of loops
Yeah.
prematurely. We have not discussed them.
Yeah.
They're not super great programming practice. It's better to do it a different way if you
While
can.
would probably be better anyway. It's just-
Yeah. So is everyone clear? Like if we start, no, so one thing that may not have been clear, let's try this just to see some stuff. So if we say our candidate prime is 2, start with is prime, what's going to happen after I run this for loop? So for candidate factor in range 2, comma candidate prime, where are we going to go after line 4? Keeping-
Test the trueness or falseness of that if statement.
So like what line number?
6.
This is a kind of a trick question.
Well, I guess I got it wrong.
Well, yes, but but you were meant to get it wrong, so don't feel bad. That's one where like, yes, the logical thing is to assume, but this is a weird case. This is one of these weird cases where like, this is going to not do what you think it's going to do, but our code worked anyway. For
I'm
the number
so
2.
curious what's going to happen.
Well, so what do we get when we do range? So first of all, what's candidate prime right now? What's its value?
2.
Right, because it's the first number we're checking for primeness. And what is range 2, comma 2?
2 to the
So that, according to how we usually interpret range, that would be all the numbers from 2 to what?
2 to 1.
Right. So how many numbers are there starting at 2 and going up to 1?
0.
Right. So if we do like, if you do something like range 2, comma 4, that's the numbers 2 and 3. If you do range 2, comma 3, that's just 2, right? Because from 2 up to 2. If you're doing range 2, comma 2, you get no numbers. You get an empty set. So what happens when you try to do a for loop through an empty set, do you think? What's your guess?
Everything's true or everything's false.
Everything's true.
So where is it? So if we try to say, normally if we had a bunch of numbers to loop through, candidate factor would get each of those numbers each time through the loop, right?
Yeah.
How many times do we go through the loop when the range returns an empty set?
Zero.
None times is the answer. So if we go to the next line, it skips right down to there, right? It doesn't go through the for loop any times because it doesn't have any things to loop through, right?
Right.
And as it turns out, because we set our starting condition to be primeness, that works for 2, right? Because like we didn't have anything to check because it's the first, like there are no numbers worth checking, which is what makes 2 prime, right? Because like 1 you don't ever check, and thus 2 by virtue of being, like 2 could not have any divisors, right? Because everybody get this? Like this makes sense, right? It's the first number after 1. All right. So that actually works in code the same reason it works mathematically, right? Because there's nothing to check to make it not prime. All right. So now we're in a more normal situation where we're checking 3. So our candidate prime is 3. We start off assuming it's prime. We're going to check what numbers in this range for what are our candidate factors now for 3.
Just 2.
Just 2, right? Because range 2, comma 3 would just give us 2. So we're going to go into this once. Now we're going to go into line 6 like we thought. We check to see if it's divisible. We think it's prime. We go back to check and see if there's anything left in our for loop. There isn't, so we go down to 11. We do the if true false thing. But here's where we ran into our first error, right? Where like we thought 4 was prime where it wasn't.
Well, it's not an error, it's just it's not error technically.
Well, it's not a like syntax error, but it is a wrong result. Yeah, it's not an error that causes Python to go like I can't read your code. Yeah, yeah, right. We don't get like an error statement. We just get it not doing what it's supposed to do. So right, we start off with our candidate factor now is 2. Our candidate prime is 4. So we start off assuming 4 is prime. We check to see if 4 is divisible by 2. It is, so we say it's not prime. But then everybody see where we run into trouble. So now we're going to check candidate factor 3. And that is not the case. So we would say it's prime, but that's not right? Because we've already invalidated its primeness due to being divisible by 2, right? So that's where we're under this problem where it thinks 4 is prime. Everybody kind of see how that works?
I have a question that might be
Sure.
like somewhat tangential, but I noticed in your output it says like, so str makes sense to me, int makes sense to me, but what is bol or boo?
Oh yeah. So yes. So a thing that can only be true or false is called a Boolean. That's named after if you ever had to do like a Boolean search in like some search engine or something, that Boolean usually means like referring to true or false kind of logic. So like if you ever do these kind of complicated, like Google doesn't do this very well I don't think Google does it at all anymore. I can't remember. Like where you say like I'm searching for this and this but not this or something like that, right? So if I'm saying like, so let's say this, like, have we done, I can't remember, have we done ands and ors already in here?
No.
Oh, so much to do. All right, so you can do and or, right? So if I want to say like, if the sky is blue and there are clouds in the sky, then do something, right? So if I want to say that is true, so like, if, let's say like a equals 3, b equals 2. If I want to say if a equals 3, and, so we're going to use 2 ampersands for this, and b,
Isn't Python just the and?
oh, is it the word and? Sorry, I'm mixing my languages here. Sorry, it's the word and, just kidding. Don't forget those double ampersands.
It's easier.
Yeah, unless you're used to every other language
Yeah.
doing it with the double ampersands. So we can test to see if two things are true at once, right? Now, if we want to see if either of these two things is true, we would do or instead. And, oops. So is that going to print out true? Is a equals 3 or b equals 2 true? Just like by the logic. Is a equals 3? Is a equal to 3?
We don't know.
Well, I just set it to
Yes,
3 up above,
yes,
yeah.
sorry.
Is b equal to 2?
Yes.
So if I say like something true or something true, is that true?
One of them's true, it's true.
Right. So if you have an or kind of statement and one thing is true, then they're both true, right? So if I say like, if a person is whatever over the age of 65 or over some weight limit, like they should get a heart examination or something, right? So like then you check either of those things, and if either of them's true, you do the thing, right? So if we do something like true or true, what does that give us? If we give true or false, what does that give us? True. If we do false or false, what does that give us? False, right? What if we do true and false? False, right? Because they have to both be true to get a true, right? Whoops, true and true, right? And false will give us what? False. It's not false equals false, because false equals false is true, right? But false and false is false. Oh, that's not, I don't remember what it is in Python. You don't have to know what XOR is. I don't even remember how you do XORs. What's that? There is another logical, so usually we only use like and, or, and I guess the other one is, what is not in Python? It's just the word not.
Not, yeah.
Have we done these? Not false, true. What if I do this? Not true or false.
False.
I mean, it's true, right? Because we know not false is true, so if it's not true or
Well,
false.
careful. So we do what's in the parentheses first, right? So true or false gives us what?
True.
And then the not of true is
False.
false.
That's tricky.
Yeah, so there's one other logical operator that I can't remember how you express it in Python called XOR, which is true when one thing is true but not the other. So like when only one of these things, it's called exclusive OR, meaning like the most literal sense of OR, like it can only be this or this but not both, right? Which is sometimes a thing you want to do. But usually you can get around. Anyway, doesn't matter. All this stuff is called Boolean logic. So named after a guy named George Boole, who kind of invented a lot of this stuff. If you ever take a philosophy logic class, which you probably won't because most of you are not undergrads, but at least when I took it, like logic was in the philosophy department, and you can do all kinds of like fun theorem proving with ands and ors and nots and so on.
This guy has XOR as exclamation equals, but isn't that not equal?
Yeah, I thought so. I don't know. It doesn't matter that much. I have rarely used exclusive or in my entire life. I usually just say if this is true and this is not true.
He's got his XOR parentheses, the two values in
And that didn't seem to work for me in Python, but oh well, doesn't matter. All right, that was a sidebar. The key thing is that that's what a bool is. That is, a bool just refers to a true-false value. Okay, so it's like a kind of variable, like an integer can only be integers, a string can be text, a float can be a decimal value, a bool can only be either true or false, right? So that's a kind of variable that you could have.
Is that for some guy named Boole?
George Boole, B-U-O-O-L-E, yep. He invented Boolean logic. I mean, he didn't invent the idea of ands and ors and stuff, but he invented like the formal analysis of statements. And you can prove all kinds of theorems. So like ifs and thens and stuff, right? So like everyone knows the classic syllogism form, like if Socrates is a man, then he is mortal. Socrates is a man, therefore he is mortal. That is what's called modus ponens in logic, meaning like if you have an if-then statement, whenever the if is true, the then must be true, right? Now, you could say Socrates is mortal. Is he a man? And the answer to that is
we don't know.
We don't know officially, right? Because the if-then is if he's a man, then he's mortal. But if he's mortal, we don't know that he's necessarily a man. He could be a dog or a cat or whatever, right? So that whole like branch of philosophical logic is like Boolean logic, and there are all these theorems you can prove about truths and falses and so on. Anyway, it doesn't matter. Where were we before we got off on Booleans?
Sorry, that
Okay,
was
no,
my fault. You
that's
were
okay.
talking about the a while statement or something.
Okay, yeah. So I think we got to why this this version doesn't work, right? So why the correct version is to take this out, right, and do this. Is everyone kind of clearish on how this works? So this should give us the correct output when we run. Kill that little guy there. When we run this version, take out the breakpoint, and just run it again. This is our prime algorithm, right? And it does work. So I guess we won't do any, like, because it's almost 3. I guess we won't do any fun leap year stuff. I was going to have us test if, like, the number of seconds since 1970 or whatever made it a leap year or not, but that's okay. So let's spend the last couple minutes that we have before we hit 3 o'clock just thinking about how we would. So it is true that this is inefficient, right? Because we could stop as soon as we find out that something is not prime. Actually, let's think about a few different ways that we can make this better. Because that's not the only way, if we start thinking about this, that we can make this algorithm better. And then maybe we'll start improving it and try a while statement next time to see if we can figure out how we could restructure this using a while instead. But so what are some reasons this is not efficient? So one is that like we keep checking numbers after we find out that something is not prime, right? Which we don't need to do.
You don't need to check any even number past 2.
Okay, so that is true. But you could also say, well, this is, so it's true that you don't have to check any even number past 2. It's also true that you don't have to check any numbers divisible by 3 after 3, right? Or any numbers divisible by 4 after 4, or any numbers divisible by 5 after 5, right? So it's true that like, so one thing that is true is like you could just check every other number, like all the odd numbers, except when you're checking evens. That's really just a specific case of the general statement, right? That things that
Right. Multiples.
multiples can be canceled out. Which leads me to, so maybe, yeah, go ahead.
Is there a way, like, if you run through this number, don't do any multiples of that number?
Ah, brilliant. All right, so exactly what I was leading up to. So maybe for the last little bit, instead of thinking about the while stuff, talk. All right. So if you're listening listening on the video, we are now in talk mode. Sorry, I'll have to dictate what we're doing. So forget about this. So this is one of the most efficient ways to find lists of prime numbers. There's some disadvantages to it. Rafi knows where I'm going by now, I think. I can't remember if you heard this already too. So let's say we're checking those numbers 2 up through 20. All right. 12, 13, 14, 15, 16, 17, 18, 19, 20. All right. So one way to do this would be, let's just to make it easy, let's say we know that 2 is prime. Because when we get to it, we haven't crossed it out yet, right? Because it's the first prime. So one thing we could do, right, if we wanted to make things more efficient, is you said, take out all the multiples of 2, right? So we go every other number, we cross out 4, 6, 8, 10, 12, 14, 16, 18, and 20, right? Now, when we get to 3, we haven't crossed it out yet if we're going up our numbers. So we say 3 is prime. We cross out every multiple of 3, right? 6, 9, 12 is already crossed out, but we'll cross it out again. 15, 18, same thing, and we're done. Is 4 prime? No, because we crossed it out, right? So we don't have to check it. We also don't have to check its multiples, right? Because if it's already been crossed out, that means all of its other multiples are already accounted for, right? Because like, if it is not prime, then previous primes have already, you know what I mean? Like, because 4 has already been crossed out, 8 and 12 and so on are also multiples of 2, right? So they are already crossed out. So 5, prime, right? Because we got to it without having crossed it out yet. And we could cross out 10 again, we could cross out 15 again, we could cross out 20 again, but they're already all crossed out. 6, don't have to check. 7's prime. 14's already crossed out. 8, 9, 10, don't need to check those. 11, prime. There's no 22. 13 is prime. 17 is prime. 19 is prime. So this is called the sieve of Eratosthenes. And it is like one of the most fast ways to find prime numbers. Just by, all you're doing is like crossing out the multiples, right? And if you come to a number which you haven't crossed out already, you know it's prime, and then you cross out its multiples, right? So that is actually a really fast way of doing this for a computer. The only downside is you have to maintain a list of all the numbers that you are thinking about and have crossed out. So if you were checking like 50 billion numbers, like if you wanted all the primes up to 50 billion, you would have to maintain like 50 billion true-false values in memory at one time, right? Because you have to like have the whole set like written down somewhere to keep crossing them out, right? So this is a method that is very fast. Possibly, I'm not sure if it is the optimally fast method, but it is.
It's supposed to be one of the best, at least like the sieve of 7. Aristotle, whatever.
Sieve of Eratosthenes. Yes, the sieve like the
Like colander?
yeah, it's like a column.
Yeah.
If you'll give me 2 seconds, I won't bother to put the screens down again. I can show you. This is actually what MATLAB uses when you ask for primes, and it can give them to you super fast. It is merely that you can only do it up to a certain number before you use up too much memory. So if we look at my like activity monitor as I do this.
like range chunks that make it.
Well, the tricky thing though is you have to maintain that record of everything you've already crossed out to know what to.
Can't you have an update, like you start a list with 50 billion, but by the time you get to 2, it's only 25 billion. And then
Yes, so you could
I mean, the
compact
list
everything.
continuously gets
that's-
smaller and smaller.
You
as
could
cross.
trim stuff out as you go along.
But you
I mean,
have to
there's
know-
there's ways you could do this, or you could like write stuff to disk and read it back in or whatever. But in terms of doing it, that's going to like hurt your doing it quickly kind of thing. But anyway, this is why like if we do this like primes 100. So this will get all the primes less than or equal to 100, and it'll tell us how long it took. Tick and Talk and MATLAB give us the time. So it takes 0.004696 seconds to do 100 primes under 100. Not much longer to do primes under 1,000. Not much longer to do primes under 100,000 or 10,000. What did I say? And 100,000. So you see, this is like super quick, right? This would take much longer. Let's do it by a factor of 100. So now we're getting up to like a little less than a second. But the tricky bit is if we look at my memory usage and see how much memory MATLAB is taking. Let's see, how much is it taking right now? So MATLAB's right now is only taking 300 megabytes. But let's watch it when we up this by a factor of 10. Oh, let's actually not do it by a factor of 10. Let's do it by a factor of 2.
This is how you broke your computer.
Yeah, it's very easy in MATLAB to suddenly start using a lot more memory than we're using. All right, so far we're okay. Let's try like doubling that. And it actually may,
10 minutes.
yeah, like I don't know how much memory it's keeping in just to like run the software, but let's see. Now it's going to take longer too. See, now the amount of memory is starting to go up pretty drastically, right? So if I want to go from, I've lost count of how many, now it is going back down again, so you have to like watch it while it's actually running this. So it's at 300 and something megabytes. Goes up to 800 something, right? So you can see that like very quickly, if you want to do high numbers, all right, yeah, I know we all got to go. Very quickly you start to run out of memory. Whereas like with the method we just did in Python, you're only keeping track of like 3 numbers in memory, right? So you're not using very much memory at all in the computer. You might keep track of like all the primes you've kept, but you don't have to.
That's using a lot more processing.
Well, so it's going to be a lot less efficient processor-wise. So that's the trade-off. Yeah. Welcome to programming. Always trading off between speed, memory usage, all the usual things you have to worry about. So oftentimes you can make stuff faster by using a whole lot of memory. But when you run out of memory, you got to either write stuff to disk or come up with ways to like express that information, like require it to be calculated rather than written down somewhere, basically, you know. So yeah, welcome to the classic dilemma. Anyway, so yeah, yes, is this something that should be on the record, or are we done?
No.
Okay, so let's cut it for today, but we can.